Herstein Abstract Algebra 3rd edition, Chapter 2, Section 1, Problem 2. In the group G defined in example 6, show that the set H, which is the set of T sub A comma B, such that A is plus or minus 1 and B is any real number, forms a group under the star of G. So before we even look at example 6, we know that a group is a set and an assigned operation star. So what this problem is asking us to do is, hey, look at this group over here, which is in example 6, which we'll get to. Look at the set and look at the operation. I'm going to modify that somehow. And here the modification is we're going to restrict the set to the set H, which is a subset of G. And then look at that subset. Look at the same operation star and tell me is H comma star a group. Remember, we abuse the notation here. We refer to the group G or the group H, but in reality what we mean is the group G comma star and the group H comma star. So now let's look at example 6. So in example 6, we're expecting to find a set G and an operation star. The set is the set of all mappings T sub A comma B of R from the reals to the reals, and here we have our actual operation. So that is A R plus B for any real number R, where A and B are real numbers, and A does not equal 0. Before we even look at the operation star, we need to make sure we understand what this set is. What does an element of G look like? In order to do that, just look at what it says. It's a set of mappings. So an element of G should be a mapping. And remember that a mapping, shown here, is a rule that assigns an element from R to an element, a unique element. So what would be an example of one such mapping? Our notation here is suggestive that R is our input variable, right? And it tells us that we're going from the reals to the reals. So R is not part of the information that we're given for an element. How do we specify an element in G, though? That's what the A comma B are. That subscript, which is not inside the open parentheses, A comma B, is what's going to determine the element. So for example, an element of this could be T sub 1 comma 2. And that element would be the map R plus 2, right? Because A equals 1 and B equals 2. That mapping, R plus 2, is one element of G, right? So when we look at the set that is H, what H does is said, okay, look at all of those elements of G. Now only focus on the ones such that A is positive or negative 1 and B is any real. So an example of an element in H could be negative 1 comma 0, which would be the map negative R plus 0. Or it could be 1 comma negative 2, which would be R minus 2. Now let's look at our operation star. So G has a operation assigned to it from the example. And the operation is just what it indicates there. T sub A comma B star T sub C comma D equals T sub AC comma AD plus B. This makes sense. Remember, an element of G is expressed as T with two subscripts. So when I say it makes sense, it means it makes sense to express an operation star between these two elements, T sub A comma B and T sub C comma D. Now, what do we need to know for this problem? We already went over what a mapping is. Here are our 4 group axioms. These are what we're going to check. And then remember that the sum or product of real numbers is always a real number. So let's check if H is closed. So to be closed, that means that given any 2 elements in the set, if we apply star, we get back an element of the set. So here, I'm just arbitrarily going to pick our subscript. So I'm saying, hey, let our first element of the set be T sub A comma B, and our second element is T sub C comma D. Normally we see that the element is just represented by one letter, but here we have this whole notation for one element of the set. And according to our rule for star, that is going to give us T sub AC comma AD plus B. Is this a member of H? Well, what are the conditions to be a member of H? We know these are mappings from R to R, right? But to be a member of H, our first subscript has to be plus or minus 1, and our second subscript has to be a real number. Here, A and C are both plus or minus 1, so their product will either be 1 or negative 1. How can I say that A and C are both plus and minus 1? Well, we started with elements of the group H, elements of the set H. So that is our assumption that A and C, because they're the first subscript in our two elements, are plus and negative 1. By the same logic, B and D are real numbers. And we have, by our claim 1.2, that AD plus B is also going to be a real number. Therefore, this new element is a member of H. Condition 2 is H associative. So here we have our two equations again, and we need to make sure that they're equal. The only difference in these equations is the parentheses. We need to apply the star inside the parentheses first, and then see if that both equations are equal. And here we just simply write it out. We take our rule star, write it out, apply inside the parentheses first, and see that indeed both of the equations are equal. Number 3, we need to find an element inside of H such that for any given element A, we have A star E equals A and E star A equals A. Now you may be asking, whoa, there is no A and there is no E. We have different notation in this problem. Correct. So we need to convert the rule or the axiom in 3 from that notation to our problem. So A becomes T sub A comma B, and I just picked A and B there. And then E becomes T sub G comma H. And again, I just picked G and H. I could have done E naught and E1 or, Y and Z, whatever you want. We need to solve for the identity element, which in this case boils down to solving for G and H. So we apply star and say, hey, the first subscript on the left-hand side of the equation has to equal the first subscript on the right-hand side of the equation. And same thing for the second subscript. In order for AG to equal A, G has to equal 1. And in order for AH plus B to always equal B, H has to equal 0. Remember that the A and B here is the element that we're given. So we don't want our identity element to ever depend on A or B. And the only way to do that, to make sure that it never depends on A or B, is for H to equal 0. And then in addition here, we need to check E star A equals A. I could have just plugged in T sub 1 comma 0 into this equation, or we can just solve for it again and make sure that T sub 1 comma 0 is the answer. And indeed it is. And you would just need to check that that is a member of our group. But the restrictions on our group is that the first subscript is plus or minus 1, which is true, and the second subscript is real, which 0 is a real number, so we're good to go. Lastly, number 4, does H and star satisfy the inverse condition? So for the inverse condition, given any element in H, so I'm letting our element be T sub A comma B in H, we need to find another element, so I'm going to call that element T sub C comma D, such that left and right multiplication of these two elements gets us back to the identity. Now the identity is always going to come from part 3. The identity element's unique, and here we know it's T sub 1 comma 0. So we just need to solve this equation, and we're solving it for C and D, and then we'll check the other side as well. So when we apply star here, we get AC equals 1, and AD plus B has to equal 0. Again, A and B were given to us, right? That was the components of the element that we started with, and we're trying to solve for C and D. So when we solve for C and D here, we get 1 over A, and then we get negative B over A. So we want to say that T sub 1 over A, comma, negative B over A is our inverse element. But what do we still need to check? There's two things we need to check to conclude that this is the correct inverse element. One, we got to make sure this is a member of the set, right? 1 over A, comma, negative B over A, it needs to be a member of H, and then we need to check the other multiplication. So let's check that it's a member of the set first. Is the first subscript 1 or negative 1? Well, we know that A is 1 or negative 1 because that was the first subscript of the element that we took out of the set. So 1 over 1 or 1 over negative 1 is always going to result with plus or minus 1. So the first subscript meets the condition to be in H. the condition for the second subscript to be an H is that it has to be a real number. Well, negative b over a, we know that b is a real number, and we know that a is plus or minus 1, so negative b over a is a real number. Therefore, we conclude that this element is at least a member of H, but we still need to check that t sub 1 over a comma negative b over a star t sub a comma b equals our identity, and indeed it does. We end up with t sub 1 comma 0. So H comma star does satisfy all four conditions of to be a group, and we are done.